Okay, we are discussing check. Okay, so you are discussing the smart sort, okay, and we have seen, okay, it requires three stage. It is the divide and conquer paradigm we are discussing, and it is consisting of three components. One is this divide, and another is this conquer. So divide, whenever we are having this list, and we are dividing it into two parts here. Okay. So to find the mid element, it might be requiring few more arithmetic operations, so it is trivial. Okay, so this division process is trivial. Conquer, so we have to recursively sort two sub-arrays here and then combine linear time merge. So we have seen that whenever we are having, say, two sorted sublists here, whenever will be having here, and this is, and then how we'll be merging that means we are combining, we are combining the two sublists into a larger one. Okay, so that is taking linear time merge, that we have are good over there. Okay. So far that was the situation. Okay, so now we have to analyze the merge sort. So this divide, again, this divide is taking trivial. That means order of one time, constant time, or theta one time, we can say. We now know what is big O, what is theta. Okay, and then conquer, we have to recursively sort two subarrays. Okay. So and this combine operation, linear time merge, that means that linear time means order of n time it will be requiring, or theta n time. Okay, so this combine operation and then this divide operation in tandem, that means with side by side they are taking how much cost, that will be coming here. Okay, so that is work dividing and combining. So this is order of n, theta n, and maybe this is theta 1. So theta n plus theta 1, again it is theta n. So divide and combining operation will be taking theta n. And then recursively we have to sort two subarrays. For that, each of the subarrays will be having n by 2, approximately n by 2 elements. So here we can use some ceiling or floor, this floor or ceiling. Okay, so something, but to make it simple, it has been shown here that, okay, let us suppose that it is exactly n by 2. So Tn by 2, and afterwards we will see master method, where we will be seeing that this floor or ceiling will not be making any kind of difference. Okay, here. So this recursively sorting two subarrays, and each of the list consisting of n by 2. Okay. So, and two sub problems we are having, two sub problems. We had this, and two sub problems we are creating, and then we are solving it. Okay. So this 2n by 2, that is coming this for this conquer operation, 2n by 2, 2tn by 2, and then divide and combine operation will be taking theta. So this is the merge sort recurrence we have got. This is the merge sort recurrence. Okay, so you see here they have solved it using master theorem. Okay, but for the time being we will not be using master theorem. We will be discussing this master theorem maybe after 2 classes. Okay, and then we will be coming here and we will be checking whether this is going by the master theorem or not. So for the time being, there is another very interesting solving technique called the substitution method. So that we will see. Substitution method that is mentioned in the CLRS. So again, we'll be telling that, okay, this is from the CLRS book. So this is from CLRS book and solution, and the previous slide is from the CLRS, that course I mentioned, so that MIT Open Courseware. So this is substitution method, and the smart sort recurrence that we have got, that is 2t n by 2 plus this theta n, plus this theta n. For the timing, what we will be doing is we'll be omitting this theta n and we'll put it here n. Okay, let us suppose that exactly this n number of comparisons are taking place during the merging process. Okay, so it is becoming much more simpler. Okay, much more simpler, and after solving this, we can take this theta n as well, and I will show you how to solve that as well. So the substitution method is a kind of guess and verify technique. Guess and verify technique. So we have to guess a solution and then we have to verify it. So this substitution method, we can say here, this is a guess and verify technique as mentioned in this CLRS. So this guess and verify technique, what we got to do, we have to guess a solution. So say I can 2t n by 2 plus n, and I am guessing a solution. Okay, let's make it little bit complicated here. Maybe we can take floor value here. Okay, so this n by 2 floor, depending on how many number of elements are there, maybe odd, even. So in that case, we can have a better estimate. Okay, which is it may not be the case that exactly n by 2 elements will be there in each of the hubs. Okay, so this 2t n by 2 floor, maybe these many elements we can have, we can think of, or we can think of ceiling as well. So 2t n by 2 ceiling, floor plus n. This can be the recurrence we can think of for merge sort right now. So now you see how to solve this with this. So first of all, we have to guess a solution. So what is the guess? So say for the time being, you have to trust me. For the time being, you have to trust me, because seeing this recurrence, what could be the guess, it may not be clear at a first glance. Okay, at a first glance it may not be clear. So how to guess a solution, that needs some kind of expertise in it. Okay, but as I am having some kind of expertise, maybe little bit, so that's why you can trust me right now. But after one class, I'll show you that how to properly guess a solution in a systematic manner. Okay, so at that time we'll be using recursion tree. Anyway, so without going into any kind of systematic approach, say you are trusting me and I am guessing the solution that Tn equal to order of n log n. Order of n log n. So this log n, this is in CLRS, this log n means log n base 2. Okay, so they are using this LGN, means log n base 2, and you know this ln, that means e base, so base will be e at that time, otherwise we will be having this 2 base. So LGN means log n base 2. So this is the guess. So that means if this is the guess, okay, so by definition of this big O notation, we can say that this implies that Tn, we have to prove that Tn less equal to C times n log n. C times n log n. We have seen that Fn less equal to C times n log n means Fn is equal to order of n log n. So that is by definition. So from here we can write this Tn less equal to C n log n. We have to prove. So this is we have to prove. We have to prove this. So we have to prove this. We have to prove that Tn less equal to Cn log n. Right. Okay. So now in this substitution method, we have to guess a solution and then we have to verify. How we will be verifying? We will be using a technique called that is method of induction. Method of induction, and that's why this is we will be seeing that master theorem may not be able to solve. What master theorem we will be discussing may not be able to solve all the recurrences, but substitution method can. Okay, so and it is relying on a very good mathematical concept called method of induction, right? So what is this method of induction? So method of induction means some base case will be true. So this, it's a three-step process. So base case is true. We have to show that some base case is true, and then we have to assume that it is true for some values, some lower values of n. It is true for some lower values of n. Some lower values of n. Lower values of values of n. Right. We have to assume that. Say, perhaps you have done this many a times in your 12th standard as well. Base case is true, then it is true for say n, and then you are proving that it is true for n plus 1. So that assume that it is true for some lower values of n, maybe n equal to n, or maybe n equals to n minus 1, or maybe n equals to k, some lower values of n, some lower values. And then we have to prove that it is true for, then prove that it is true for some higher values. Okay, true for some higher values, for some higher values. So this is the three-step process that we have to remember for this verifying process. Okay, so now we can we have done this Tn less equal to Cn log n. So we have to prove this Tn less equal to C times n log n. Right. So we have to take that it is true for some lower values. So now we have to go back to this recurrence. Okay. So this is the bottleneck. That means we don't know the value. We are assuming that it is true for some lower values. So our lower values is floor n by 2. Okay. So n equals to, say, let us suppose that it is true for n equal to floor n by 2. That means for some lower values of n, right, it is true, so that we can substitute that value here, and ultimately we have to prove that this condition we are reaching. Okay. So considering this recurrence, and considering the recurrence that it is Tn by 2 floor, so let us suppose, assume that it is true for n by 2 floor. N by 2 floor. So it is true for this. So now this, if it is true for this, then what we are getting, we have to put instead of n this n by 2 floor. So n by 2 floor I am doing, right? So it will be less equal to this c times n by 2 floor, n by 2 floor times, so here I am putting, instead of n I am putting n by 2 floor, and this is log n by 2 floor, right? So we have got this. Now we have to put 2 times this value there in our original equation. So maybe we can little bit we can process this, as we have to substitute that 2t n by 2 floor. We can do this, less equal to c times, so say this both to this side will be coming as well. We are multiplying both side by 2, n by 2 floor, and then this log n by 2 floor. So this is the thing, and maybe we can add 2t n by 2 floor plus n, both side I am adding n, so 2c n by 2 floor times log n by 2 floor. Okay, so we have got this, and you see in the previous slide we had this. Okay, so we had this in the previous slide. We'll be substituting that value here. Okay, we are starting from this, and then we have got this, and then we will be substituting whatever values I have got, and let's see what is happening. So Tn, that is equal to 2t n by 2 floor plus n, and now what we are getting? We are getting that this is less equal to this, so we are putting that value 2 times c times n by 2 floor times log n by 2. Okay, so this is plus n will be here, both side I am adding, so both side I am adding plus n, so this will be plus n. And now you see that floor n by 2, it is less equal to n by 2, that you know, right? So floor n by 2 less than this, less than or equal to this n by 2. So that inequality will be utilizing here, and we will be omitting this floor as soon as possible, because that floor and ceiling are very annoying. Okay, so you have to omit that as quickly as possible, so that our life becoming easier, right? So we can write that this is less equal to 2c n by 2. So instead of this by this inequality, you have to write here by this inequality times this log n by 2 plus n. Okay, so now you see, so this 2 and 2 cancelled out, so this cn and this log n by 2, we can write this is log n minus log 2, right? Log a by b plus n. So you see this, here I have got less equal to sign, and here I have got less equal to sign, right? But here I have got equal sign. That you have to remember. So what we are doing here, I am omitting the floor value. Here I am omitting the floor value, and I am taking somewhat larger values. So that's why this whole term is less equal to this term, okay? But in this third line, I am only, what I am doing? I am only manipulating something. I am only simplifying something, not manipulating. I am manipulating, but here the second to third line I am only simplifying it. Okay? I am not adding or deleting any kind of extra thing. So that's why this is equal to this. Okay, this is equal to this. Okay, so this is we can write. So Tn here I don't have any space, so I am writing this line and then this line here. So less equal to 2 C n by 2 times log n by 2 plus n, right? And here I am writing, so 2 cancelled out. So Cn log n minus log 2 plus n. Okay, then I am again simplifying Cn, sorry, this Cn times log n, minus Cn times log 2. So log 2 is, who will be telling what will be the value of log 2? Saurabh, you tell. Saurabh, what is the value of log 2? Huh? Log 2. Are you searching in the net? Who will be telling what is the value of log 2? It's base 2. Log 2 base 2. Then why you are so late? Huh? So log 2 is 1. So 1 times Cn. 1 times Cn is Cn, and then plus n is there. So now we are having Cn log n minus, so this is Cn minus n. So minus, I have taken minus common, and then this is Cn minus n. So now can I say that this is less equal to Cn log n? So you see, this is Cn log n minus some positive quantity, and that is, say I am almost telling that x minus, say, 5 is less equal to x. That is what I am telling here. So x minus some kind of positive quantity, will it be less equal to x? Definitely. So that is there, but we have to have the case that Cn minus n, in that case Cn minus n should be greater equals to 0. Okay, greater equals to 0. Then Cn log n minus 0 at worst case. So it will be equaling Cn log n, and Cn log n minus more positive quantity, then we will be having this Cn log n minus some positive quantity, that will be definitely less equal to Cn log n. So Cn minus n greater equals to 0. So that means Cn greater equals to n. Dividing throughout by n, we are getting C greater equals to 1. So for C greater equals to 1, this quantity will be definitely greater equals to 0. Okay, so then this inequality is getting satisfied, right? So what we have eventually got, Tn less equal to, we started with the equation, equation, and then we have got this one by this substitution method. Okay, so Tn, ultimately we have got the Tn, we had to prove that Tn less equal to Cn log n, and that we have proved here. That we have proved here. And then we can say that this Tn, the merge sort recurrence, ultimately it will be n log n, order of n log n, right? So this is the case. And now say I am little bit complicating it, 2t n by 2, maybe this floor is there, plus this theta n. Theta n is there. So now what we got to do is theta n, you know that theta n means it is less equal to some c times n. Okay, that we have seen in the earlier classes. It is less equal to c times n. So as we are doing the worst case analysis, we are substituting the highest value is c times n or less. So I will be substituting that the highest value, then we are safe in analysis. Okay, we are going by the worst case analysis. So this theta n we will be substituting by Cn. Okay, we will be substituting by Cn, and then we will be guessing the solution that Tn equal to order of n log n, the same thing, order of n log n. And then we have to prove that Tn is less equal to, here I have got one constant, that is Cn, that is coming from this expression. So for the overall constant, we will be taking not Cn, we will be utilizing another constant, that is dn log n. dn log. Okay. So here this, and then I'll be assuming that it is true for this lower value of n, right? Tn, so less equal to say Tn by 2 floor, so dn by 2 floor. The similar analysis is going on here, only the difference is that we are substituting it by Cn. So now we are getting that this is less equal to 2t, sorry, not t, this value I am putting here. So d times n by 2 floor log n by 2 floor plus Cn. Then I can say this is 2d, we are omitting floor, this plus Cn. And the similar thing is going on, 2 cancelled out, so it's dn log n minus 2, so dn log n minus log 2 means 1, so it will be dn plus Cn. So that is equal to this dn log n minus this this n I am taking common here. I am taking this minus common here, that would be better. So this dn minus Cn, and then I can write that this is less equal to dn log n, provided that this quantity dn minus Cn greater or equals to 0. That means dn greater or equals to Cn, and that means dividing throughout by n, we are getting d greater or equals to c. So whatever c I am having here, say this c is 2, then I will be taking d as 2 or more. Then this condition, this thing will be satisfied, and that is this d is the overall constant. So whatever if I am seeing the whatever constant I see here, then I will be choosing that constant or more. That liberty I am having. So this if it is theta n, then I have to substitute that with its highest upper bound, that is Cn, and then we have to proceed likewise. Okay, we have to proceed likewise. So we'll be getting the solution, right? Okay. So this is the case. As this, you see this Tn equal to theta n log n they are getting. So theta means it is both big O notation, it is signifying that order notation, and then omega notation as well. So both the condition getting satisfied. So you can say that theta n log n means this order of n log n. So both the condition will be satisfied, then only we can say it is theta n log n. So we'll be going by the master theorem afterwards as well. So now I'll be ending this this lecture with another problem that is called this binary search. Okay, so find an element in a sorted array. Find an element in the sorted array. So we have an array and we are having some elements down there, say maybe 1, maybe 10, maybe 12, maybe 2, maybe 3, and say I am searching whether 2 is there or not, whether this 2 is there or not in this array A, maybe. But for binary search it should be sorted one. This is unsorted, right? So now this array will not be given, will be given a sorted array, and then we can think of for binary search. Otherwise we cannot think of this binary search. So 1, 2, 3 and 10 and 11. So this time I can apply this binary search technique on this array. Okay, so what we have to do, we have to divide. That means we have to check the middle element. What is the middle element? We have to find out the middle element, and based on that we have to divide afterwards. So we have to find out the middle element, and then we have to check the middle element is equal to this element. That means the element I am searching. If I am not finding, the middle element is not equaling, then recursively we have to search one subarray. Either this subarray or this subarray we have to search. And then combine operation, there is no combine operation involved as such here, so combine operation is trivial. Okay. In the previous case, the merge sort, we had the two sorted subarrays and that subarrays to be merged. And at that time, combine operation took a substantial amount of time, that is theta n or order of n. But here, as such, no such combine operation we will be having. We have to, if I find that middle element, we have to return that only. Okay, so this here is an example given. Say this array, this is the sorted array. Okay. And 3, 5, 7, 8, 9, 12 and 15, and we have to find 9 here. Okay. So first of all, we have to find the mid element. We have to find the mid element, and mid element is 8. And then 8 will be compared with this 9. Is it equal? No. And then what we got to do? We have to search in this sublist. Because we know that if this is 9 and 9 is greater than this 8. So all the elements which are coming here will be less than 8. So there is no point searching in this because we will never find this element here. So that's why we have to, depending on whether this element is less than or greater than this, we have to decide which subarray we have to take in the next iteration, okay, for searching. So as 9 is greater than 8, we have to definitely search here in this. So 9, 12 and 15, okay. Then we have to find out the middle element of this subarray again. So that is done here. So middle element. And then we have to compare this 9 with this 12. 9 with this 12. Is it equal? No. But this time this 9 is less than 12. So definitely we have to come back to this sublist. And that is exactly being done here. Okay. And then only one element is there, so that we have to check that element with this 9, and 9 is equaling 9. So we have found that element. Found. So this is the binary search, and remember, this binary search only will be applicable when the array is sorted. When the array is sorted. Otherwise, we cannot apply this binary search. As you know already, this is a very common searching technique, and you know this type of question comes in interview, that you are having one unsorted array. Can we apply binary search in that? So at that time you should not be telling we can. Okay, we cannot have binary search on an unsorted array. This is again and again I am repeating. You should not be telling that. Okay. So this the recurrence for binary search is this. So Tn is equal to, as you have seen, only one subproblems I am creating and one subproblems I am recursing. So this is 1. In the merge sort case it was 2. Okay. And the subproblem size, as you have seen, that it is n by 2 approximately. We can use floor and ceiling to have a better feeling that what exactly, depending on odd even numbers, that will be having the thing. So if I am writing n by 2, okay, it is okay. Subproblem size, it is approximately n by 2. And then the work for dividing and combining, as we have seen, combining is almost nothing, and this divide only we are finding the mid element. That's it. And then we are having maybe 1, and then this we are having one comparison operation. Okay. So divide and this combine operation, we are having theta 1 time. Okay. That means constant amount of time. So this is our recurrence. This is our recurrence. Tn equals to Tn by 2 plus this theta 1. Right. So whenever theta 1 is there, this is less equal to some constant. So this you can put some constant over here, okay, as the upper bound, and you can analyze this. So you solve this by guess and verify technique in your hostel today, right? So we'll be seeing many more examples in the next class regarding this divide and conquer algorithm, and we'll be seeing some more solutions. Say maybe if I am having a floor out here, then how we can go out there. So maybe we can take up, or I can give you that as an exercise as well. Okay, we'll be seeing many more examples in the next class. So if you have any question, you can ask me. Okay. Today only. That's good question. This today only. Say after this class, I'm sitting for an hour, for half an hour, and then I am letting you know, especially to Saurabh, and Saurabh will communicate. Sorry, what? Enrollment key. Okay, if it is required, I will send. Otherwise, you can directly join. Ah. Okay. That I will be doing.